joining today. The main objective of this presentation will be to provide an overview of the entire process for how material solutions are selected and integrated into automotive battery components. We'll be starting from the initial design phases all the way through to repair and disassembly at end of component or battery life. So I'll give a brief introduction on Henkel and the technologies we focus on, and then we'll dive right into how material solutions are selected and optimized for individual applications within the electric vehicle market. We'll talk about how they're applied and integrated into the manufacturing process, and how debonding adhesives can support repair and end-of-life considerations like recycling. So Henkel is a global consumer brand and specialty chemical company headquartered in Dusseldorf, Germany. Consumer brands include household and beauty products you probably use in your home, such as like Dial soap and Snuggle fabric softener. My team is in the specialty chemical division, which specializes primarily in adhesives, sealants, and coatings. The Loctite brand is usually the most commonly known for things like super glues and thread lockers. But there's a lot more to the adhesives division, though, than those on-the-shelf items that you find while out shopping, like in home improvement types of stores. We have many divisions that cover almost any industry you can think of. So cars, computers, airplanes, construction, and packaging are just a few of those examples. Within the automotive division that I support, we have several different teams focused on different mobility areas. So think vehicle interior, exterior, cameras, and other components for autonomous driving, and eMobility are a few of the primary focuses. And then within my team focused on eMobility, we specialize specifically on power conversion systems, e-drive systems, and of course batteries, which I'll be talking you through in today's presentation. So there are many different adhesive technologies that support the build and lifetime performance of automotive batteries. Some of the main ones are listed here, and I'll quickly highlight the purpose of each. So starting with conductive coatings up in the top left corner, these are thin coatings utilized in dry battery electrode manufacturing to improve conductivity, enhance adhesion, and basically provide a layer of protection. So next, moving clockwise, we have assembly adhesives, which can be used for virtually any part of the vehicle, with different products being formulated to bond specific different substrates and under specific environmental conditions. Battery safety coatings are an area of active investigation for us, and they serve as basically a protective shield against the spread of heat and fire. Gasketing has a lot of similar considerations as assembly adhesives, and they come in different forms. So examples of those would be like cure-in-place gaskets versus form-in-place gaskets, depending on considerations such as build speed required and part serviceability. Dielectric coatings are thin coatings that can serve as an alternative to PET to provide electrical insulation. We also have a wide range of traditional structural adhesives, as well as some new innovations that are designed to debond on command, which I'll spend some time going over towards the end of the presentation. And last technology I'll mention is thermal interface materials, such as thermally conductive adhesives and thermal gap fillers. And these are used to basically dissipate heat or enhance heat transfer. So thermally conductive adhesives and gap fillers are just two types of thermal materials that we offer. The primary difference between these two being that the thermally conductive adhesives also have structural integrity. But they come in other forms as well, such as gap pads, which are basically the solid version of gap fillers, as well as greases and phase change materials. And all these solutions are designed to be applicable to different cell types, so prismatic, cylindrical, and pouch. So now that we covered some kind of general background, we can jump into how we begin the material selection process for each unique application we support. And we use thermal interface material selection as an example, and I'll continue to build on that example throughout the rest of the slides, and as we discuss the overall process. So first things first, we want to work with you to understand what your application is and what the performance requirements of the adhesives are to meet your performance needs. So in the case of thermal interface materials, thermal performance is obviously one of the first things we consider, as well as other material properties like adhesion strength, preferred cured mechanism, environmental testing requirements, and any other standards that you may test to, like for example, flammability rating. Then we consider how the material should be applied and how it will fit into your manufacturing process. So this includes aspects like mechanical gap and tolerances, substrate type and surface preparation, and really any other considerations for various processing steps or preferences, targets that you're trying to meet. Finally, we want to consider how adhesives with structural bonding capacity will impact repairability and eventually recyclability. We want to consider this in the early design phase so that the adhesive specifically formulated to debond can be used and to ensure that the component design allows the bond line to be accessed by the tools required for the debonding. There are a few different methods for debonding that we'll cover shortly or towards the end of the presentation. I'll detail that process as well, but generally speaking, in addition to strong performance over lifetime and on-demand debonding when required, we've also strived to ensure that the adhesive is manufacturing friendly during application and also during the removal. So once we determine the adhesive technology best suited for an application, so for example, like the physical form being a thermally conductive adhesive versus a thermal gap filler, we'll usually next determine the most suitable chemistry type. So in our team, the portfolio primarily consists of silicones, polyurethanes, acrylics, epoxies, and some hybrid technologies. These categories apply to many technologies, not just thermal interface materials, but I'll touch on each one of them quickly. So silicones are basically the go-to when high temperatures are requested, and they typically perform very well in terms of flexibility and elongation. And therefore, they perform really well in terms of like testing like vibration resistance. Additionally, our silicone portfolio also includes low VOC silicone solutions to support specific regulatory targets. Next, looking at polyurethanes. These are a very versatile chemistry type, and they're both tough and also provide more flexibility than, say, acrylics and epoxies. Acrylics and especially epoxies are typically selected in instances where you basically need the stronger, harder, and more chemically resistant material options. And then finally, hybrids, which, like the name implies, are kind of a combination of properties of different chemistry types to achieve desired material performance parameters. And an example of that would be like modified silanes. So as you can see from the overview of the chemistry types, and then as you dive deeper into each chemistry and compare different products within each of those categories, there's a balance or a trade-off between different aspects. So strength, thermal conductivity, cure time, and many other properties have to be tuned and tweaked relative to each other. And that's where the expertise of our product development teams really come in. The main building blocks that we consider when creating products that meet different priorities are shown here, and they are physical form, filler, and resin. Basically, the resin is the liquid portion that gives characteristics such as temperature stability, adhesion strength, and cure time. Fillers are the solid particles that are added to provide specific additional properties like thermal conductivity, electrical isolation, and helping to establish or maintain a specific bond line thickness. And then physical form is basically referring to which product family is best for things like assembly force and conformability required in an application. So examples of this would be like gap pad versus gap filler, or thermally conductive adhesive again. Okay, so after requirements definition, we can move on to the topic of modeling and simulation, with the goal of this being to develop the best solution for each application as quickly as possible. So we work with you as early in the development as we can to fully understand the material characteristics and performance needs that we previously defined and to develop a tailored formula for that. So speed is critical with the constantly evolving technology trends in the EV market And with each market innovation comes its own technical challenges in terms of material solutions that may require entirely new material selections or specific individualized adjustments to current ones. So we have a video here on this slide to provide a short introduction and some nice visuals that'll give a little bit more background on the concept.
The EV market is evolving rapidly with shorter innovation cycles and increasing regulations. But consumers are demanding even faster development, compressing innovation cycles down to just 20 months. Henkel makes this possible with state-of-the-art modeling and simulation solutions, accelerating material selection and development. With a comprehensive portfolio of advanced materials, Henkel solutions drive performance, safety, and circularity in battery systems. Now, with AI-driven modeling and simulation, we collaborate with OEMs and battery manufacturers early in the design phase to speed up development. Through material application simulation, we optimize dispensing patterns to reduce waste and speed up production. Structural simulation improves designs for lighter, stronger, more durable battery packs using structural adhesives. Thermal simulation selects the right thermal materials to deliver efficient heat dissipation for faster charging and longer battery life. At Henkel's in-house battery test center, we validate these simulations under real-life conditions. The result? Faster development, accelerated designs, fewer iterations, and a shorter time to market. From advanced materials to cutting-edge simulation, Henkel is innovating for zero-emission mobility.
Okay, so again, the first step is determining the requirements. Then what we want to do next is translate those material properties and requirements into a virtual formulation and a virtual material card. This allows us to predict the behavior of that formula or new material before actually making and testing it in the lab. Once we have an understanding at the material level of how that formula performs on its own, then we can test those material cards in virtual customer models to predict performance in their specific designs. So basically in the intended real-world scenario. This data and information assists in each step of the battery design process. So first in feasibility studies, where it's quick and easy to try out different material options and formula adjustments. Then with the materials that seem to be a possible fit, we can facilitate proof of concept validation of things like thermal and mechanical requirements. We can also aid in the design calculations to determine performance requirements or changes to those initially set, such as structural and thermal targets. And then simulating the resulting material selection, which is a major cost and time savings versus the traditional method of going straight to the lab tests with materials going straight onto customer components. And finally, making tweaks or optimizations based on the results. This slide shows kind of the material level workflow, which lays out the aspects that we just discussed. So material characterization, material card creation, modeling, and then the validation of that modeling using simulation, and then of course, experimental testing. So looking a little further into what is accomplished in each step and how they build upon each other. In the material characterization step, we are determining independent material behavior. So things like rheological, structural, and thermal properties under given test conditions. So basically, how will the material perform or likely respond in standard tests, such as like lab shear strength, modulus, and other material property lab assessments. Then throughout the modeling and simulation, we're taking the material card and basically putting that into specific or customer scenarios. So this allows us to evaluate the material in different disciplines like structural and thermal performance in specific component level scenarios. And then once we have that virtual representation of the real world scenario, we can confirm the material performance with the in-lab physical testing of both the material and battery level. And this last diagram on the modeling and simulation topic basically just compares the classic formula or the classic development cycle with our cycle utilizing these virtual tools. So historically, each formula adjustment would have to be made and tested in the lab first in order to create a material card. And then we could begin the validation steps from there. This could consist of several different formulations for a given project, meaning several rounds of these steps. And for those of us that have worked in the labs, we can appreciate what a time-consuming process it can be to run a series of experiments like this, versus now looking at the newer approach where the virtual formulas of interest can be put right into customer models without having to spend time or resources on any, physical mixing and testing. And from there is where we begin the lab work of actually making the formula, testing and validating it. So main point here is that we can have a pretty good idea of how a formula will perform before ever having to actually make it, which makes the development process much more efficient. So now that we've worked through how we can quickly create different formulations, we come to the last step of the material selection process, which is final selection and validation of a formula. Here we consider basically the same types of information that we cover in requirements definition, but we need to revisit them and ensure the material we've developed works as a whole in the customer system and in meeting bigger overarching topics. So component design, chemical makeup, performance parameters, those are examples of the key determinants that we initially reviewed that need to be tested and met both at the initial battery level testing as well as after environmental testing. Cost is, of course, a factor, as well as ensuring the material dispensing and curing is optimized for and fits into your process, hopefully improves it. And lastly, ensuring that we meet any sustainability standards that the market is striving to meet. So now that we have the optimal material designed, it's tested, and it's ready to be implemented and integrated into the manufacturing line, we can shift our focus onto making sure that the material is used properly so that it can actually perform as intended. Of course, the inherent abilities of the material are there, but they also need to be dispensed and handled in a way that I guess maintains those properties. So in addition to our product development teams, we also have application engineering teams that are dedicated to supporting the implementation of the material solution selected. So this includes things like supporting trials in our labs and conducting additional tests, helping to choose dispensing equipment partners, and being there once equipment arrives to ensure a smooth startup with the material. Also optimizing the process and parameters on the line, answering technical questions, and then they continue to support throughout future use of the material as well. So any questions once a material is up and running, those are also addressed by them. We have many Henkel labs throughout the globe where these and other teams sit, but we have 2 labs that are dedicated solely to innovation of materials for batteries. The first is located at our headquarters in Dusseldorf, Germany, where we have both a battery application center and a battery test center. And we recently opened a new facility in Madison Heights, Michigan as well. That has a battery application engineering center with similar capabilities to the one in Germany, along with a center of excellence for functional coatings, which includes a couple of the technologies that we covered in the beginning, like dielectric coatings and conductive coatings. Elaborating a little more on the capabilities at the Madison Heights, Michigan lab, it was basically designed to replicate an industrial environment. So this consists of a 6-axis high-capacity robot that helps our application engineering teams get ahead on the optimization of dispensing parameters before it even goes into any equipment or goes to a customer facility. And then also trialing or prototyping initial parts before actually going onto the line. We can dispense 1- and 2-part materials and all the chemistry types that we touched in the beginning, as well as many technology types, such as thermal interface materials, gaskets, sealants, and structural adhesives. And we handle packaging sizes here all the way down from cartridges for prototyping up to drums. So the takeaway here is that we have local support to speed up testing cycles for product development and implementation of new materials. And Madison Heights is also where a lot of our product development team is based. So that makes for a much easier cross-functional collaboration between the teams. We're excited to welcome OEMs and battery manufacturers to visit Madison Heights and tour the battery lab. So on the right is a QR code that you can scan if interested. So I'll leave just a second for anyone that's interested to scan. And now we can move on to the last topic, which is debonding. So far, I've been focusing on how to select a material solution and how we can support and ensure that it will work on the manufacturing line and continue to work throughout the lifetime of the component or battery. But what happens if there's a need to make repairs online? And what about battery disassembly at the end of life? These are very hot topics for us right now, as we're seeing the need to innovate to support both cost savings during battery repair and eventually recyclability to support a circular economy. So because of these topics, we've come up with a solution in the form of debondable adhesives. These are considered design-in rather than drop-in options. And we say they need to be designed in for reasons like ensuring that the tooling required for debonding can access the bond line and that the correct substrates are selected. This short video will provide a little bit of an introduction into the technology before we dive in and basically just explain what it is a bit more.
As EV battery production grows, so does the challenge of end-of-life batteries. Henkel's adhesives enable automated debonding on demand, streamlining repair, reuse, and recycling. In a typical repair, the workshop removes the battery from the vehicle, unfastening the screws and detaching the lid from the sealant to access the cell stacks. With bond strength up to 12 megapascals, Henkel's patented debond on demand adhesive enables highly automated disassembly at ambient temperature. Precise application of voltage at designated conductive points triggers electrical delamination using Henkel's HEDL technology. As the current gradually decreases, debonding completes, allowing for non-destructive disassembly of the cell stack from the pack. After surface preparation, fresh debondable adhesive from Henkel is applied as a liquid, film, or tape. Next, a new cell stack is added, and the battery pack is resealed. The battery is reinstalled, ready to power the vehicle again. Henkel is driving the future of battery circularity, enabling smarter repairs, longer battery life, and less waste. Henkel's debond on demand adhesive enables high automation, ambient temperature processing, clear progress monitoring, and clean surfaces ready for rebonding, turning waste into renewal.
So there are two primary debonding mechanisms we see as optimal for the automotive space. One being the electrical delamination that was demonstrated in the video, and the other being thermal delamination or debonding. Thermal debonding is selected as a best option for some components within the vehicle, and it utilizes the application of localized heat to the bond line of the debondable adhesive, which basically softens the material, causes it to foam, and makes it easy to pull apart or disassemble. Trigger temperature is adjustable to fall outside of the component's operating temperature, so we make sure there's no unintended debonding occurring during operation. And then looking at electrical delamination, it is a room temperature option, which instead breaks down the material by applying voltage rather than heat. So this method is typically more suited for battery applications, and it can be adapted for different battery configurations and cell types and on different types, for example, of like cooling components. A little bit of a deeper dive into how electrical delamination works. We're weakening the bond by ion diffusion, which is initiated by applying voltage to the two electrically conductive substrates in contact with the bond line. So it's crucial that the two substrates are electrically conductive, of course. Like in thermal delamination, the result is an easy to disassemble part, and the parameters such as voltage and time can be customized. So one interesting thing about this method is that you can basically measure or read the progress of the debonding as it's happening, because the current converges to 0 amps, indicating the completion of debonding. So then at that point, the material can be peeled off both substrates, leaving behind 2 clean surfaces. Just like other more typical aspects of requirements definition and solution selection, individual applications may require either of the 2 mechanisms, thermal or electrical, and the selected solution will need to be tailored further to account for where the material is applied in the vehicle or battery, what the battery configuration looks like, and what types of cells are used. And of course, knowing the end goal or primary purpose that you are interested in the debonding for can help in the design consideration phase as well. Now looking at system layout, or how to design an assembly compatible with electrical debonding. The simplest option would be if the 2 substrates that the debonding adhesive is going between are electrically conductive, and then it can just be applied directly there. For instance, like if you're using it to bond an aluminum substrate to a cooling plate. The setup shown in the image here, however, shows a layout example when the 2 substrates we wish to bond are not electrically conductive, such as the case shown in the image between battery module and cooling plate. The adhesive basically comes in 2 forms, either a thermally conductive adhesive version or a purely structural version. For the thermally conductive version, we're reaching strengths of around 3.6 MPa, but we're achieving strengths up to about 10 to 12 for the purely structural material. You can see the before versus after debond comparison of lap shear strength on the graph at the bottom right, where that 3.6 MPa in use strength for the thermally conductive material reduces to virtually 0 after the voltage is applied. Thermal conductivity of the thermally conductive adhesive is something that can be adjusted depending on the performance requirements, and it's currently at about 1.3 watts per meter Kelvin. And of course, the materials have been tested to the same typical aging and stability standards that we use in other typical automotive applications, such as heat and humidity aging and cycling. Lastly, before we wrap up, I wanted to invite everyone attending the battery show in October to stop by our booth number 2200. You'll be able to walk through the material selection process that I just went through with you today from beginning to end, as well as talk to some of our experts in each of those individual areas. We included a QR code for anyone that hasn't registered yet, as well as a promo code for a discount at registration. So I'll give everybody just a second to scan that if interested. And then with that, I'll just, thank everybody again for their time and attending today. And thank you again to Volta for hosting and giving me the opportunity to share this information today. My contact information is here for anyone in case anyone wants to connect or has any questions that they'd like to reach out about. But I'm happy to open it up to questions at this time. So thank you.
Great. Thank you so much, Brianna, for your presentation. We'll open up the floor to questions. Brianna, you can go ahead and stop sharing and we can just have like a Q&A session here. I see already a lot of questions in the Q&A section here, so thank you for that. I'm sure there are more in the audience, so if you want to ask a question, use the button on the bottom of your screen, and then you can ask your questions here. And Brianna, if you want to come onto video, we can have you answer some questions at your selection.
Yes, my computer just wasn't. Here we go. Now I made it.
There you go. You're back. Awesome. Brianna, we have a question. Are your thermal conductive materials suitable for thermal setting plastics? This is from Ravi Menon.
Okay, yeah. So the thermally conductive adhesives, like with structural adhesives, we have different chemistries and different products that are formulated for different substrates. So that would be an example of when we would pull in the application engineering team to, find specific products or possibly develop specific products if we didn't have them to meet those specific, requirements.
Cute. Um, Scott Fisher asked about the virtual material card. So for the virtual material card, do you generate the dynamic mode data and structural data for each formula, or do you interpolate for classes? Classes of polymers, I'm assuming.
Sorry, can you repeat the question one more time?
For the virtual material card, do you generate the dynamic, I guess, model data and structural data for each formula, or do you interpolate for classes of polymers and binders?
So I know we do different levels of material cards. Exactly how they do the modeling would be more of a question for our modeling team. But that's something I can certainly take to them and, follow up with if someone wants to reach out.
Sounds good. Um, Seeing some more questions coming in. So, Jamie Hughes asked, how do timelines and qualification steps change between innovation levels, e.g., like phase A, phase B, phase D, phase D, and where D is a direct drop-in substitute, no change to SOP, and A is prototype.
Okay, so am I understanding is it the timeline comparison between just choosing like an off-the-shelf option versus going through the development cycle?
Yeah,
Yeah, so drop-in options can be done very quickly. Again, that's really the application engineering team's specialty. It's selecting a product, and then we can begin immediately doing any validation testing or supporting any validation testing that would be required. As far as the development cycle for, brand new materials, that varies quite a bit. First of all, we consider customer SOP, and then we kind of base the timeline from that. So, we have all different, standards and processes that we have to meet, but the timeline for those can be, just adjusted depending on the timeline that's required.
perfect. Okay. Um, we have another question for slide 13. Do you want to pull that up really quick for everyone to see? This is a question on regulation and certification. Someone asked where does regulation certification fit in this process?
Here we go. Okay, and what was the question where we start
Uh,
considering regulations?
yeah, regulation and certifications.
Yeah, so any regulations that we want to meet or any standards that we want to meet, that'll be something that we want to consider as early as possible. So as far left as we can. The more we know up front, the easier it is for us to, consider these different aspects and make sure that they're prioritized. Because again, everything is kind of a trade-off, right? So if we know kind of wants versus needs right from the beginning, then we can formulate based off of those priorities.
Perfect, thank you. Scott Fisher asked for materials with a cure condition dependent material properties. How do you handle this in the virtual material cards? Um,
Oh,
yeah,
sorry. My screen went.
no
Sorry, one
worries.
more time.
Scott Fisher asked for materials that have specific cure conditions depending on the material properties. How does the virtual material card handle this difference in these sensitive parameters?
Um, So I guess that would be something that would be put into the material card. So
Mm,
I know like with like looking at the real world scenario in the lab, um, like we may recommend a cure time of, X amount of time at Y temperature, for example, for a heat cure. But if those are changed, that could result in a slightly different material, or it could result in slightly different, material properties of that material. So all of those inputs would have to be considered in order to accurately represent the material.
Gotcha. Okay. I have a quick question on my own. There's a lot of pending regulation in Europe for uh, these sort of materials and recyclability and circularity. Do you expect this to also translate over to US regulation, and what will be the impact of that, especially with bonding materials?
Yeah, so again, Henkel's a global company. Our customers are global. So the regulations that are coming from Europe, that's something that we're considering now rather than later. We want to be proactive rather than reactive, so that if and when those do make their way here, we'll already be implementing it. But again, because our customers are global, a lot of times, or a lot of customers are, that's something that we, just want to work on upfront too.
Okay, that makes sense. Yeah, this seems like, especially in the circularity space, Europe is driving a lot of the changes, and it'll ripple out into the rest of the industry.
Right.
Um, Sami had a question about form factor. So Sami asks, are the debonding mechanisms better suited for a specific battery type? For example, cylindrical, prismatic, or is it the same across the board?
Not necessarily. So again, that would be a consideration for maybe how we would, want to tweak the method, or how we would do it for an application specifically. But those are all options. We can consider all battery types.
That's good. I think having specific binders for each form factor is quite important in different
Right.
parameters. Yes. Priyanka asked the question a little bit left field, but do you also provide conductive coatings for battery current collectors? So binders for inside the battery for Henkel
Yes, we
solutions.
do offer conductive coatings. And again, we recently opened a new facility specifically for functional coatings in the Madison Heights, Michigan facility. So we have a whole PD team that's dedicated to supporting those types of materials.
Perfect. Okay. Um, Ray asked a question about electrical delamination, about the voltage ranges. So for the electrical delamination process, is there a like a working voltage range that the battery will be delaminated? And if like, for example, the battery insulation failure, will the battery be like accidentally come apart from the pack?
Yeah, so that's a really good example of why we consider them to be design in rather than drop in, so that we can consider all of those things so there's no accidental debonding in life. So that's something that we don't want to just recommend a material for. We want to make sure that the design is compatible, right? So that's one of the number one considerations. And then the voltage could be adjustable, but the total time as of right now is a matter of minutes with application of voltage. And then by the time that the material is ready to be peeled off and again comes off clean. So these are all things that we can work with individual applications on.
Perfect. Um, I have a question from Connie Chen. First, she says, "Thank you. Thanks a lot for inspiring talk." Connie was wondering at Henkel what level of battery modeling is most commonly used. So at the material level, cell level, at the pack module level, or system level. And is Henkel focusing more on new material optimization or to make existing EV batteries more reliable? And there's a second part, but I'll let you answer that first.
Okay, yeah. So as far as I can speak more on the like material level for the modeling, and again, the modeling team would probably have more. Well, they would have more in-depth information as to like how they're actually running these models. But we do both like I guess more like static and dynamic material card levels 1 through 3 for these new materials. Um, so and then system wise, I would have to get maybe a little bit more clarity on. But what was the second part of the question?
Uh, is Henkel focusing efforts on making new materials and optimizing those materials or making existing battery systems more reliable?
I think it's a combination of both. I think the goal is, of course, to make the overall systems better, and then we want to make materials that make that possible, or better materials that can actually optimize or perform with these newer innovations like higher temperatures, electrical considerations, things like that. So I think it's first we look at what the part needs to do, and then how we can make a material that can make that possible.
Hmm, gotcha. Okay. Connie also asks if there's a battery department in Dusseldorf, I'm assuming in Germany, and uh, she's also curious on how do you collaborate with the US battery department?
Yes, so actually the Dusseldorf lab was the first battery lab. I believe it opened, it was a few years ago,
Hmm,
22, 23. And then we just basically replicated that here in North America this year.
got it. Okay. And I'm assuming to collaborate with the US battery department, Connie should reach out to you.
Yeah.
Perfect. All right. And we've posted Brianna's email in the chat if you'd like to reach out to her after the event. If you have any other like collaboration or interest in the presentation itself. We have a couple of other questions here. Suram asks, what techniques do you use to quantify adhesion? Like, is there any sort of tests that you can provide that is standard for this kind of material?
Yeah, there are a lot of different ways. So one of the most common ones is lap shear strength, which basically consists of bonding two substrates together, clamping them and pulling them apart. And that's in like a shear direction. We also do, um, kind of more um, like peel testing is another example. Um, we do different kinds of bonded joints and pull those apart and determine the force that's required to pull them apart. So we look at all different types of application of forces. We also look at if the failure mechanism was cohesive or adhesive, because that can tell us a little bit about if the failure occurred due to the substrates or if it was due to the inherent material ability. We can look at the effect of different, pre-treatments, surface roughness, all those kinds of things can be put into that question. So again, that's another thing where like the testing capabilities that we have really are very, very useful, because one material, you could put it on three different places and you could get three different, strength numbers. So that's something that we consider for the individual system.
Gotcha. Okay, thank you. Pablo has asked, is the HEDL material electrically conductive, and does that property change during delamination?
Electrical properties shouldn't change during delamination. So basically, whenever you bond the part, and I can get a little bit more specific technical information from the PD team on this, but basically when you apply the voltage or the heat, it can be peeled off, so it stays like a solid material. It just no longer is sticking to the two parts, if that makes sense.
Yeah, that makes sense. Um, Scott also asks for the reversible bonding options. How clean is the debonding? Do you need like a second cleaning step as well to prepare the surface for new adhesive, or is it just resticking back on?
Yeah, so it's very minimal. I would, and again, it would depend on the application, but we always want the cleanest surface possible. So even if it's just like a quick IPA or acetone wipe or something like that, and I'm talking like lab substrates, but sometimes just a quick wipe is enough if it's even required. Um, so it would just depend on the individual application, but very, very minimal, pre-treatment in between.
Gotcha. Okay. I think that's most of the questions we have here. Virginia just asked a question. In developing the debonding processes, are you working with battery recyclers?
Um, as far as who we're working with, maybe we could reach out to talk about that if there's anybody that has questions.
Okay, perfect. Let's see. I think that's I think that's most of the questions we have that are related to this topic. If you have more questions, please do reach out to Brianna. Again, her email is in the chat. Um, but I think that will conclude our webinar for today. Thank you so much, everyone, for joining. Thank you, Brianna, for the wonderful presentation. And thank you for the Henkel team for putting on this webinar for us.
Yeah, thank you so much, Michael, and thank you, everyone.